Yay!
Yay! All right, one more sort of classic problem in static equilibrium that we can treat is called the leaning ladder. So here's the setup. I've got this ladder leaning up against the wall. What we suppose is that it's a smooth wall, so we won't worry about friction between the ladder and the wall. The only friction in the problem is down here between the ladder and the ground. And so what we want to know is, what's the minimum angle until this ladder starts to slip? I mean, the more vertical the ladder is, the bigger the angle theta. You get the idea that maybe the ladder is more stable because there's not as much frictional force. But if you try to get the ladder, if you try to make theta too small, then there's too much frictional force with the ground exceeding the coefficient of friction with the ground, and so the ladder might slip. That's the idea. So knowing what the coefficient of friction is, let's see if we can find out what the angle is, the minimum angle of sort of lean for the ladder before it slips. Okay, so once again, what you want is you want the sum at static equilibrium. So you know that we want all the forces to sum to zero and all the torques to sum to zero. Here's the problem. I don't really know right now what the forces are on the ground or the normal force from the wall. Right? There's two normal forces. There's a normal force from the wall, normal force from the ground. The trouble is that I don't know what the frictional force from the ground is either. So the strategy is let's sum the torques about the ground, because that'll zero out those two forces. So the strategy is I'm going to zero out those two forces by taking the torques about that point, because the R is 0 down there. I'm going to solve for the normal force for the wall. That'll be the one unknown that I don't know yet. We're supposing we know the mass of the ladder and the length of the ladder. So I'm going to solve for NW. And then knowing that, I can come back up to my force equations and then solve for the frictional force with the ground. And hopefully I'll be able to solve for theta then. Okay, so let's sum the torques about the ground. Let's see. About the ground, I'm going to have, it looks like two. There's two torques. So one of them is the normal force from the wall, and that's going to, about the ground, that force is trying to make the ladder rotate clockwise. I'm going to call that negative. So that's going to be, how far away is it? It's going to be, it's negative, it's L away. And it's N W, but not all of it, right? We want the perpendicular bit. The perpendicular bit of NW is going to be NW sine theta, because as theta goes to 0, I'm going to have no torque. That's the way to think about it, right? Because NW then will be pointing along the ladder. So this is going to be NW sine theta is going to be that torque. Okay, and then mg, the weight of the ladder about the ground, is going to try to make this thing spin counterclockwise about the point. So that's going to be a plus. So it's going to be plus. The center of mass is L over 2 times mg. Okay. And this is going to be equal to 0. Okay, so let's see what I got. Well, it turns out that the L's, I can just factor out an L and then divide it away. So it looks like NW is just going to be mg over 2 sine theta. Okay. So now that I know that, oh, I forgot something, didn't I? It's not mg. Looks like I made a mistake. Okay, look. It's not because mg is not perpendicular to the ladder. I want the perpendicular bit. We just got done saying that for NW. So what is the perpendicular bit of mg? Well, what happens if theta is 0? When theta is 0, I want all of mg. Mg will be perpendicular then. So it looks like when theta is 0, I want the whole thing, so that's cosine. So this is going to be mg cosine 0 equals 0. Okay, neat. So it looks like that's going to be in 2mg over tangent theta, then goes to the bottom. So I'm going to have something that looks like that, mg over 2 tangent theta. Okay. Yeah, because it's cosine over sine, so that's over tangent theta. Cool. All right, so now I know what NW is, but that must, look at the forces. The only other force in the x direction is little f. So in the x direction, the sum of the forces in the x direction being equal to 0 means that NW is going one way and F, our frictional force, is the other way. And our frictional force is just mu times Ng. Okay, so it looks like mu, I'm going to substitute NW in over here, so mu N times the normal and the ground, mg over 2 tangent theta. Okay, very cool. And then look what we have here. The sum of the forces in the y direction summing to 0. Well, what forces are in the y direction? It looks like all I've got is Ng going up and mg going down. So there we go. So mu times mg, substituting that in, is just mg over 2 tangent theta. Well, the mg's go away. It's kind of cool that the mass of the ladder and the length of the ladder don't even matter. They just divide right out. So this tells me that tangent of theta is just going to be what? 1 over 2 mu. So theta, that critical angle theta, is just going to be the inverse tangent of 1 over 2 mu. Okay, that's nice and simple. Let's box that up. If mu is 0.4, sort of a typical mu with respect to the ground, then theta turns out to be, I think it's something like, what did I get, 51 degrees. Something like that. So if the angle is greater than 51 degrees, then you don't slip. Everything is all right. If it's less than 51 degrees and mu is just 0.4, then you're in trouble. Then it'll start to slip on the ground. Okay, cool.